am Akashdeep Kaur, and today I am going to talk about remote core power management in asymmetric multiprocessing systems. So, disclaimer, this is a technology presentation, not product readiness or roadmap commitment. Opinions presented here are of individuals, and they may not represent that of Texas Instruments. So, about Texas Instruments. Texas Instruments believes in collaborative culture that is centered around upstream first approach. So, we do believe that whatever we build in-house should be upstreamed. So, TI is actively working in many open source projects, including Linux Foundation, Yocto projects, Ambien, U-Boot, and many others. So, introduction to speakers. So I am working as a software engineer at Texas Instruments. I primarily work on low power management in Sitara SoCs, which includes working on security firmwares, device management firmwares, U-Boot, and TFA. So my co-authors are Hari Nagala, who is also a software engineer at Texas Instruments. He primarily works in U-Boot, TFA, Linux driver development, and on Sitara SoCs as well. So my second co-author is Kendall Willis, who is also a software engineer at Texas Instruments, and she also works primarily on power management for our Sitara SoCs, and she works on U-Boot, TFA, and Linux driver development as well. So unfortunately, they could not travel today for the talk, so I will be presenting it on their behalf as well. So, okay, so let us discuss about the agenda. The agenda for today would be, we will start with a quick introduction about the problem statement, and then we will continue to understand what are the existing device driver power management operations provided by Linux kernel, and then we will try to understand what are the possible solutions and what is the selected solution for the remoteproc suspend resume implementation. And finally, we will try to wrap it up with the additional challenges or the improvisations that can be done. So now let's try to understand the problem statement. But before that, what are asymmetric multiprocessing systems? So basically, typically in modern SoCs, we have asymmetric multiprocessing setup that is designed to run diverse tasks such as real-time operations that run alongside general purpose workloads by employing different core types. This really helps to increase the efficiency and performance because we make sure that the right core is doing the right job. So these systems typically include a host core, which typically runs a rich operating system that is Linux. And then there are some remote cores, which includes microcontrollers, C7X, or any other generic cores which are doing the operations such that the best core is doing the job in a good manner. Okay. So here you see a block diagram. This is TI's AM62A SoC. So on this SoC, we have application cores, that is ARM core cluster, which is running Linux. Then we have device management. There are real-time cores which are designated for various purposes. For example, there is a device management core which is meant to do device management operations, which include power management operations and some resource management operations. Then there is some application-specific cores like MCU cores, which are typically running some RTOS-based applications. And we also have DSP core on this SoC, which runs some signal processing. Now, what is remoteproc firmware, which we call remote processor framework in Linux? It manages the life cycle of all these remote cores, which includes starting a core, stopping a core, late attach, and it is also responsible to manage the power on these remote cores during the suspend and resume of system. Okay, so now let's try to understand the problem statement. So typically, Linux supports 4 sleep states, which include hibernation, suspend to idle, suspend to RAM, and standby. 3 of these states is relevant for ARM processors. So these are hibernation. So in typically this hibernation, the system will suspend and it will save the context to a disk, which can be SD or eMMC. And whenever the system resumes, the context will be restored. And the second state which Linux supports is suspend to idle. So suspend to idle state is something like in which the user space gets frozen and all the system enters into a suspend mode, but the primary CPUs are not switched off. So basically, whatever deepest idle mode is modeled in device tree, the system will enter into that state. So we have one more low power mode that is like sleep state that is supported by kernel, which is suspend to RAM. So in this sleep state, the kernel will save the context to RAM, and it will also switch off the primary CPUs. And these are the three states. Now, there can be SoCs out there, for example, TI's AM62A SoC, which supports multiple low power modes. So in this table, we can see there are 3 low power modes written. The first one is deep sleep low power mode. So in this low power mode, our entire SoC is switched off. Only the DM core is running so as to wake the SoC up from the low power mode. And the entire context is saved to RAM, and then it is restored during resume. There is a second low power mode which we call as MCU only mode. In this mode, in addition to the configuration of deep sleep, MCU core is kept on to run some background tasks so as to monitor the system operations. And also we have a third low power mode which is IO only plus DDR. So basically in this mode, the SoC suspends, the entire SoC is powered off, only some IOs and RAM is kept in self refresh so as to save the context. So basically if we see, these 3 low power modes are all different variations of same suspend to RAM mode that is supported by Linux. So now how will the remoteproc driver decide on what needs to be done during the suspend and resume of each low power mode? Because it cannot differentiate, the Linux cannot differentiate.
I just need to move the mic.
Yeah, thank you.
Don't be too close to it, and it's
Okay.
going to be better.
Okay, thanks.
Yeah, keep going, sorry.
Okay, yeah, thanks. Yeah, so how will the remoteproc driver? It's not. Yeah, okay. So how will the remoteproc driver decides on what needs to be done in suspend and resume? So basically, how will it differentiate?
Can everyone hear? Okay.
But it's my own voice, so it's okay.
Try now.
Yeah, I can try. It's not moving in this direction. Okay, it's okay.
It has to be a little closer.
Yeah. You need to move further away.
Okay,
There you go. And just speak.
okay. So now if you see in all the low power modes, the remote cores have different requirements. So here we are listing all the remote cores that we saw in the first slide, which includes MCU R5, some DSP and DMR5. So if you see and compare in each low power mode, the requirement of the remote core is different. In some state, the remote core needs to be powered off. In some cases, they need to be running. So it is different. And the remoteproc needs to take care of all of these remote cores while it is going to suspend and also while resuming from the low power modes. Okay, so now let us do a recap of device driver power management options which are present in the kernel. So basically, typically there are 2 models in which you can put the device drivers into low power states. So these models include the system sleep model, which is the first model. So basically, it depends on when you are going to put your device into low power state. So if you put the device into low power state while the system is entering the system-wide suspend, then we call it the first model, which is system sleep model. But in the second model, the devices are put into low power mode when they are in runtime, when they are running, the system is running. So basically, it happens independently. Devices can individually enter into low power state independently of any other PM activity, which is in principle. So now, in this presentation, we will be primarily focusing on the system sleep model because that is what we are going to discuss about. To know more about runtime power management, you can refer to good talks by Kevin Hillman and by Shreya Patel. So now we will go into the model 1 and the suspend part of model 1. Okay. So basically, typically the system suspend resume happens in several phases. So in all these phases includes executing callbacks of devices before the next phase begins. How is the ordering ensured then? Basically, the ordering follows the device hierarchy. The devices, the time at which the devices are registered matters when these suspend resume callbacks are called. Basically, in suspend phases, in short, the device hierarchy is traversed in bottom-up order. That means a child has to be suspended before the parent. And during resume phases, it is traversed in the top-down order. That is, a parent needs to be resumed before the child has resumed. So that is the typical flow, but it can vary for 1-2 phases. So let us now try to understand each and every phase. So the system, whenever this phases start, basically the first phase which starts is the prepare phase. So in this phase, after this, no new devices can get registered. Basically, no new nodes are created after the prepare callback method returns. So the second phase, which is suspend phase, can be responsible for doing multiple operations. So it can typically stop the device from performing any I/O operation, or it can enable wake up on that device, or it can even save the device registers and put the device into low power state. But still, it depends on the system and the architecture. It can vary on every device. So now all or some of the operations can be done by suspend late callback as well. So it depends on the system and any other dependencies that which work you want to give to which callback. So next we have suspend no IRQ phase, which basically is used to perform any operations which you need to do after the IRQs are disabled. So in that case, suspend no IRQ callbacks can be called. After that, your system, there is some platform specific code that gets executed, and then your system will finally enter into a sleep mode, and some wake up event comes that triggers the system to wake up from that low power state, and then some platform specific code which will finally hook to the resume no IRQ phase. Now, in this resume no IRQ phase, basically, whatever was done in the suspend no IRQ phase will be reversed. So that is whatever operation needs to be done that needs to be done before the interrupts are enabled will be performed. After that, we have resume early phase. In this resume early phase, whatever was done in the suspend late, or it can vary also, it still depends on the device architecture. So basically after that, resume callbacks are called. In resume callbacks, the devices can perform I/O after this, I/O operations after this, and we can do any other resume code can be done so that the device is now out of low power state. Finally, we have the complete callback, which essentially undoes the operations which were done by the prepare sleep callbacks. Now, every device can register these callbacks using this structure dev pm ops in the kernel, and they can just give a pointer of this structure to the device driver structure as well. So basically, these callbacks will take care of now what happens if some operations needs to be done before the prepare callback is called or after the complete callback is called. In that case, we need to have something different. So for that, we have something which we call power management notifiers. So basically, there are some operations which need the entire user space to be available before that operation can be executed, and that cannot be done by PM callbacks that we just now discussed, because some devices may not be available, and they also have to be carried out while the system is fully functional. So basically for that, the subsystems or drivers can register the suspend notifiers, which will be called on the two events, which is before prepare, when the system is preparing for suspend. So in that case, it can be called, or it can be called after the system has fully resumed. So still it depends on the architecture, and this can be used whenever it is required. Okay, so now let us try to understand what is the implementation. But before that, just summarizing that, the problem statement is how will remoteproc driver differentiate between different low power states. So this is option 1, which can be one of the possibility of implementing based on whether the wake up is enabled from that remote core or not. So basically what can be done is, using sysfs interface, the wake up can be enabled for that remote core. Then the remoteproc driver can check whether the wake up is enabled using that may wake up function. So on the basis of if the wake up is enabled, then it will notify about the remote core firmware about the suspend, that system is going into suspend, and remote core firmware will understand that okay, now I have to stay on. But the second option, if the wake up is disabled, then in that case the remoteproc driver can simply use the shutdown message, which is typically used to runtime suspend the remote core firmware also. So in that case it will send the shutdown message and then it will power off the remote core. So this can be one option. So this option is also good, but for a SoC like AM62A, this will not work because we don't have only two low power modes. We have more than two low power modes, and this mode is also Linux. This wake up enabled or disabled, this is all Linux dictated. Linux is simply telling the remote core that okay, now you go to suspend, now you go to shutdown state, and also the remote core will not get to know that whether I am going to suspend or not in the second case, because it's just getting a shutdown message. So if it has to execute some code which needs to be done in a particular low power mode, it will not be able to do that. So that is the problem, that it will not be able to differentiate between more than two low power modes. So now, before we try to understand and deep dive into the solution, let us try to understand some of the abbreviations that we are going to use. So first is TISCI, which is Texas Instruments System Control Interface. That is essentially some message passing protocol which is used by kernel to interact with device manager or security manager firmware. The next jargon that we are going to use is DM. So DM is the device management core, which is responsible to handle all the low power mode operations. And the third term that we are going to use is constraints. So constraints is something that restricts your low power mode entry. So that can be, from the device driver's point of view, that can be some PMQoS request, which essentially is what is the maximum resume latency, what is the latency in which you want wake up, like after how much time the system will resume. The second one is device wake up, which is whether the wake up is enabled from a particular device or not. So all these constraints can restrict the system from entering into a particular low power mode. And this can also include the setting of constraints for CPU QoS, constraints which can include the CPU resume latency. So now let's try to understand the solution. So basically now we are trying to understand the flow, but that needs to, the solution needs to come after the flow because it is related to flow. So typically during a low power mode entry, that is system suspend, we start it with by writing the mem into syspower state file. The system starts suspending. So as discussed earlier, if any driver has the suspend notifier, that will get called first, followed by the prepare callbacks and then the suspend callbacks. Now we have the DM, which is device manager, and there is RTOS application. So RTOS application can also set constraints. In our current solution, the RTOS application, that is the remote core firmware which is running, can also set the constraints and send it over to device manager during boot or during resume. And after that, when the Linux driver starts suspending, there is this TISCI PM domains driver, which is responsible for managing power domains using GenPD framework. So this driver starts to suspend, and also the TISCI driver. These drivers aggregate constraints from devices as well as CPUs. So these constraints, as we discussed, can be wake-up constraints or the latency constraints. So they will aggregate all the constraints and send it over to device manager. Now, finally, from TISCI driver, there is a prepare sleep message that is sent to DM to indicate that now Linux is going to enter into low power state. At that point, the DM will look over all the constraints and select the perfect low power mode for this operation depending on the hardware and what it can support. So according to that, DM will lock the low power mode that the SoC is going to enter. After that, the Linux will continue its suspend, other drivers will suspend, and after that, the remoteproc suspend late callback will be called. We are not calling it in the suspend phase because the remote proc solution that we have implemented needs to get the logged mode from device manager, which is only done after which can only be done after the suspend callbacks are over. So basically, this is the solution. So the solution is that on the top is the remote proc driver, and on the bottom there is a remote core firmware. So what happens is the remote proc driver sends a suspend message to remote core firmware. So it gets to know, okay, I am going into some low power state. Now the remote core firmware independently will go and query the DM about what is the low power mode I am going to enter. So according to that, it will send a response to remote proc driver. So it depends completely on the vendor implementation, what they want to do in the remote core firmware. But at least they should be able to receive this suspend message from the remote proc driver, and also they should send a response back. So basically in our case, the response can be ACK or auto. So if the response is ACK, that means I am ready to go to shutdown, please shut me down. So basically the remote proc driver will execute the shutdown sequence, which is it sends a shutdown message to remote core firmware. And then the remote core firmware is in low power state. But there is a second option, which is auto option. In the auto option, the remote core firmware can, it is just telling the remote proc driver that, okay, I will take care of myself. If I want to stay on, I will stay on. If I want to turn myself off, I will turn myself off. It completely depends on the remote core firmware, what it needs to do now. So basically, in this case, the remote core firmware can have whatever it needs to do in a particular low power mode. So it can differentiate and it can simply do its job. Okay, so now there are some other drivers whose suspend late callbacks get called, followed by suspend no IRQ callback. Then finally, platform specific code gets executed and DM executes the code to enter low power mode. Now, during the resume, now we have to resume the firmware. In this case, DM code executes to resume the system, followed by a platform specific code, and then some resume no IRQ callbacks will get called, followed by resume early callbacks, and finally the driver complete callbacks will get called. Now after this, if there are any post suspend notifiers, they will get called. In our case, we are executing the remote core firmware loading in the post notifier because our hardware architecture is such that we are dependent on the resume callback of one driver. So because of that reasons, we need that mailbox driver to be IP to be available before we execute the reloading of firmware. Because of that reasons, we have used PM post suspend notifier in the resume path. So basically in this case also, the remote proc driver will query about the remote core's current state from the device manager. Device manager will respond with whatever the state is. If it is on, then the remote proc driver will simply notify the remote core firmware that, okay, I am up now. You can send me any messages if you want to. So that is done by sending some echo request message to remote core firmware. And then the remote core firmware will get notified about that Linux has resumed. In the other case, in which the current state is off, the remote proc driver will just restore the device configuration, which can vary from SoC to SoC, and then it will reload the firmware. So this is just what we have discussed right now. So basically, from the remote proc driver point of view, you need to register the device power management operation hooks, and it depends completely on the architecture where you are going to support this. It may not be suspend late for you, it can be suspend for you, or it can even be before that. So it completely depends on the architecture where you are implementing the solution. So basically here, as I discussed earlier, that we are going to, on the basis of the response received from the remote core firmware, the remote proc driver will take an action, and then it will update the state in the kernel that, okay, what is the state of my remote proc. So after that, basically this is one snippet which is just showing the callback for PM suspend notification which you need to add in case your hardware also has dependency on some of the drivers. But this can also be some resume callback as well. It completely varies from architecture to architecture. Okay. So these all changes which are required to support the low power mode on the remoteproc drivers are not yet upstreamed, but the upstreaming will be done in the coming cycles because the remoteproc driver was refactored and it was just recently upstreamed. So we will upstream the remoteproc changes for low power modes in the coming cycles. So now let us try to discuss the additional challenges which we can face. So challenges which you can get when you are trying to get suspend resume working in remoteproc systems. So the first challenge nowadays, there is a lot of a need for early booted remote cores because of the evolving system. So for that we need to have some solution because the remote cores which are booted early may not support LPM. The reasons for that can be because if the Linux file system does not have the same remote core firmware which was packaged in U-boot or SPL binary, in that case, how will the remoteproc driver have access to that? So in that case, there can be multiple options which can be solutions which can be implemented, which can be either you can save and restore the context, or you can just, you can have the same copy of whatever was loaded and packaged. So there can be multiple solutions, but it's still an open problem. So, and it still depends on hardware. Some hardwares may have this support, but still this is something that needs to be looked into. Now the next thing can be, so second point is not really a challenge, it depends on architecture. It's just some problems you will face when you are implementing the suspend resume on remoteproc driver for the first time. So some of that challenges can be, if your hardware is not in a clean state, in that case your system it can prevent your system from entering into suspend state. So there can be any of the problems that you can face. The first problem can be, there can be unread messages in various FIFOs which can prevent the system from suspending, and also it can be because the remote cores does not have IPC support. So there are some messages which are just tail messages, but they are just preventing the suspend. Or it can be that the RP message channel was not properly suspended by the user space application. So all these things need to be taken care whenever you are implementing this remoteproc driver suspend resume implementation in your code. See, these are the references. So I would like to thank Texas Instruments for giving me this opportunity to present, and Linux Foundation to provide the platform, and Bailey Bray for the collaboration and support in implementing this solution. So, open for questions.
Do you see any point in, so from my point of view, you define constraints in Linux that you pass on to the DM firmware?
We can also define constraints in the remote,
Yes, yeah. Yeah, so you define constraint in Linux or in the DM coming from RTOS. Do you, and those don't come back to Linux, right? Linux is not aware of constraints that are put on by the RTOS.
By some other code?
Yes. Is that an issue to you, and
no,
do you plan on addressing that?
First, can you repeat his question so everyone is able to hear it?
Okay. So his question is that, so Linux may not be aware of constraints that other entities in the system is putting and sending to device manager. So is there any issue in that? So there is no issue in that, because the thing is, whenever the prepare sleep message goes from Linux to DM, then DM does respond and log the state. So if any driver has the problem, then like for example, if the remoteproc driver has the problem, whenever the remote core firmware starts suspending, it will query the state. If it thinks that the state is not good for me, it can send a cancel message to remoteproc driver and the suspend can abort. Suspend will not go through. So basically every entity will have their say in the system, but if any entity has a problem, then we have a way of aborting the suspend as well.
So you have your own setup, or you've talked about is TI specific. Do you have any discussions in line for synchronizing what every vendor does? Maybe others want to do an approach that is similar. They might not use the same DM, but maybe we can want to think in the same way from the Linux kernel point of view. Is there any discussion in that direction, or are you alone in the fight?
Right now we are alone, and I will say, yeah.
You can use S2 idle.
Yeah, that is what I was going to say. We can use the S2 idle and model the different states in the device tree.
You can refer to morning top.
Yeah.
Also, the constraint subsystem is not TI specific, right?
Yes. Yeah, but that was my first question.
Yeah.
If it doesn't come back to Linux, then Linux is not the master of the
Yeah,
state
Linux.
that will reach, and that can be an issue for decision making.
But
Well,
this
it's
is,
a master of
yeah.
the state of all the IPs that it is already managing. It's not managing the RTOS anyway, so it doesn't get the DM is the
Manager,
DM is the final
yeah.
decision maker, not Linux.
Yes.
Linux is just one of the major players.
Yeah. Okay. Any other questions? Yeah.
Yeah, it might be a silly question, but ARM already provide SCMI, which is the system control management interface. So what is the difference between your proposal and your TI-SCI and ARM SCMI?
So basically, yeah, so his question is that ARM is already providing SCMI. So what is the difference between the ARM's implementation and the solution that we have provided? So basically, in our case, what we are doing is, okay, so you are trying to say that the platform specific code. So in our case, typically we have all the information about the system, which includes like which are the devices which will be on, which will be off in that particular low power state with device manager itself. So because of that reasons, the device manager is itself deciding the low power mode, rather than having the full device configuration. And so basically we have today device manager on AM62 family is managing the full power, which includes it is aware of what are the devices and everything. So if we have to implement this solution using that approach, then we will have to migrate the entire information to the ATF code maybe. So which is not feasible in our case because we already have device manager which is aware of the full system. So it's better to leverage the device manager itself and use it for the decision making rather than using the SCMI approach for this SoCs. Maybe for the other SoCs in which the ARM trusted firmware code is aware of the device configuration, that solution can be implemented. So it completely depends on the SoC. And also like what is the state, which is the manager which is having all the power, like which is having the awareness of devices and everything. So it depends completely on that.
Just a bit of history, TI-SCI protocol actually precedes the SCMI protocol. So we have been using this TI-SCI protocol even before SCMI came out, which is why we are continuing to do our solution on that. But in future devices like the AM62L, we have to use
Yeah.
SCMI.
Okay. Any other last minute questions? Okay. Thank you.